In machine learning, not every problem has a continuous numerical answer. Sometimes the answer is binary, yes or no, 0 or 1. Is this email spam? Is this tumor malignant? Will this customer default? These are classification problems, and the algorithm designed for them is logistic regression. Today we build it from first principles: the sigmoid function, the probabilistic model, the cross-entropy loss, maximum likelihood estimation, gradient descent, the confusion matrix, the ROC curve, everything derived mathematically, implemented in Python, evaluated on real medical data. Let us begin. The fundamental problem with linear regression for classification is simple. It predicts values outside the range 0 to 1. A probability of -0.3 or 1.8 is meaningless. We need a function that squashes any real number into the interval 0 to 1. That function is the sigmoid. Sigma of z equals 1 divided by 1 plus e to the power of -z. Let us examine its properties carefully. As z approaches positive infinity, sigma approaches 1. As z approaches negative infinity, sigma approaches 0. And at z equals 0, sigma is exactly 0.5. This is the midpoint, the natural decision threshold. The derivative of the sigmoid is also elegant. Sigma of z times 1 minus sigma of z. This property makes backpropagation computationally efficient, a fact we will use in neural networks. The logistic regression model applies the sigmoid to a linear combination of features. P of y equals 1 given x equals sigma of w transpose x plus b. Let us be precise about what this means. W is the weight vector, 1 weight per input feature. B is the bias term, the intercept. W transpose x plus b is the linear combination, exactly like linear regression. Then sigma squashes this into a probability between 0 and 1. If that probability exceeds 0.5, we predict class 1. Below 0.5, we predict class 0. The boundary where the probability is exactly 0.5 is called the decision boundary. In 2 dimensions, this is a straight line. In higher dimensions, it becomes a hyperplane. This is what makes logistic regression a linear classifier. The decision boundary is always linear. How do we train the model? We need a cost function. The natural choice would be mean squared error, but this is a mistake. When you compose sigmoid with MSE, the resulting loss surface is non-convex. It has multiple local minima. Gradient descent cannot reliably find the global minimum. We need a convex loss function. Enter binary cross-entropy, also known as log loss. The intuition is elegant. If the true label is 1, we penalize with negative log of y hat. If y hat is close to 1, perfect prediction, the loss is near 0. If y hat is close to 0, catastrophically wrong, the loss approaches infinity. Similarly for the case when the true label is 0. Both cases are combined into one equation. J equals -1 over n times the sum of y times log y hat plus 1 minus y times log of 1 minus y hat. This is convex. Gradient descent is guaranteed to find the global minimum. Why is cross-entropy the right loss function? This is not arbitrary. It has a deep probabilistic justification. The answer comes from maximum likelihood estimation. Given our data, we want to find the parameters W that make our observations most probable. The likelihood of observing all our labels simultaneously is a product over all samples. Taking the logarithm converts the product into a sum, numerically stable and easier to optimize. Maximizing this log likelihood is mathematically identical to minimizing the cross-entropy loss. This is profound. Logistic regression with cross-entropy loss is not a heuristic choice. It is the statistically optimal estimator for binary classification under the Bernoulli distribution. Every parameter you learn by minimizing cross-entropy is a maximum likelihood estimate. Training logistic regression means minimizing the cross-entropy loss using gradient descent. The gradient of J with respect to the weights has a beautiful closed form. The partial derivative of J with respect to W equals 1 over N times X transpose times Y hat minus Y. Notice something remarkable. This is structurally identical to the gradient in linear regression. The only difference is that Y hat now passes through the sigmoid function. The weight update rule follows directly. W new equals W old minus alpha times 1 over N times X transpose times the error vector. We repeat this for every epoch. The loss decreases monotonically because the loss surface is convex. When the loss stops decreasing, training is complete. The model has found the weights that maximize the likelihood of the observed data. Let us implement this in Python. We use the breast cancer Wisconsin dataset, 569 patients, 30 features, binary outcome, malignant or benign. Step 1. Load and split the data. 80% training, 20% testing. Step 2. Standardize features. This is essential for gradient descent convergence. Step 3. Train. Logistic regression from scikit-learn with max iterations set to 1000. Step 4. Predict both class labels and probabilities. Step 5. Evaluate. Our model achieves 98.2% accuracy on the test set. That is 113 out of 114 test patients correctly classified. The full Jupyter notebook with every line of code is linked in the description. Run it. Modify it. That is how you build real understanding. Accuracy alone is not enough, especially in medical diagnosis. Imagine a model that predicts everyone is healthy. On a dataset with 95% healthy patients, it achieves 95% accuracy. But it is completely useless. It catches 0 sick patients. The confusion matrix reveals the full picture. True positives, sick patients correctly identified as sick. True negatives, healthy patients correctly identified as healthy. False positives, healthy patients incorrectly flagged as sick. Type 1 error. False negatives, sick patients incorrectly classified as healthy. Type 2 error. The dangerous one. From these 4 numbers, we derive 3 essential metrics. Precision of all patients we flagged as sick. How many truly were sick? Recall of all patients who were truly sick. How many did we catch? F1 score, the harmonic mean of precision and recall. The balanced metric. In medical applications, recall is paramount. Missing a malignant tumor is far more dangerous than a false alarm. The ROC curve gives us a complete picture of the classifier's performance across all possible thresholds. ROC stands for Receiver Operating Characteristic. The x-axis is the false positive rate, how often we incorrectly flag healthy patients. The y-axis is the true positive rate, also called recall, how often we correctly identify sick patients. At every threshold from 0 to 1, we plot 1 point on this curve. The diagonal line represents a random classifier. AUC equals 0.5. A perfect classifier hugs the top left corner. AUC equals 1.0. Our logistic regression model achieves AUC of 0.98 on the breast cancer dataset. This means, across all possible decision thresholds, our model nearly perfectly separates the 2 classes. AUC is threshold independent. It measures the fundamental discriminative power of the model. Use it to compare classifiers regardless of the operating threshold. Logistic regression. From first principles to production. Today you derived and implemented everything. The sigmoid function squashing to 0 and 1. The logistic model probability output from a linear combination. Binary cross-entropy loss, the mathematically correct cost function. Maximum likelihood estimation, the statistical foundation. Gradient descent, finding the optimal weights. The confusion matrix, precision, recall, and F1. The ROC curve and AUC, the gold standard for binary classifiers. The Jupyter notebook, complete Python source, and all figures are linked below. Tomorrow, day 4. Neural networks. When linear boundaries are not enough. Subscribe. 1 rigorous lecture every day. See you tomorrow.